All right, welcome back. And now that we are done with chapter 2, we'll move on to the next chapter, and this will form part of lecture 3. And so we are moving on to probability. So probability is a very interesting subject. Okay, so we'll start with probability, then we'll go into the Bayes theorem. From there, we'll go into probability distributions, sampling distributions after that, and we start confidence intervals. Okay, so that is how we're going to move. But in this lecture, we have probability. So we start with just basic probability. So I want you to have an idea of the meaning of some terms that we use in probability. Experiment. Okay, so an experiment is just a process of obtaining outcomes for uncertain events. Okay, so this process of obtaining outcomes for uncertain events is just known as an experiment. Also, terms such as the sample space. So the sample space is just the collection of all possible outcomes. Okay, now some of the things that we're going to use are, say, maybe a coin. Okay, tossing a coin, casting a die, and drawing a card from a deck of cards. Okay, so you need to know what a coin is. Of course we know. So a coin has only two outcomes, that is a head and a tail. Okay, so the collection of all possible outcomes, we're saying that it is a sample space. So when you have a set containing a head and a tail, then you know that you have a sample space for the coin. Okay, a die has 6 faces. A deck of cards has 52 cards, okay, of which 26 are black and the other 26 are red. Okay, so you have to know cards like an S, the card that has an A, okay, that is an S card. All right, so those are some of the things that we'll be using. Another term that I would want you to know is an elementary. Okay, maybe let's start with just an event. Okay, so let's have an elementary. An elementary event. Okay, so this is just an outcome from a sample space with one characteristic. So it's an outcome from a sample space with one characteristic. Okay, so an example is drawing an S from a deck of cards. So drawing an S from a deck of cards is an elementary event because it is a possibility with one outcome, okay, with one characteristic. And then if we're going to say maybe drawing a card that is black, okay, that is also an elementary event because it's an outcome with just one characteristic. Okay, so we move to an event now. An event, this is an outcome. Okay, so it's an outcome from the sample space of course, that may okay, so this may involve two or more characteristics. Actually, it's two or more outcomes simultaneously. Okay, so an example is drawing an S that is also red. Okay. So in this case, we have two outcomes occurring simultaneously. Okay, so now we move to the definition of probability. Now, probability is the chance or likelihood that an uncertain event will occur. Okay, and it is always between 0 and 1. Okay, so this is the definition of probability. It is just the chance or likelihood that an event will occur. Okay, now we use the formula. The probability that event EI, it can be E1, E2, we're just saying an event. Okay, it's just equal to the number. Okay, let me just shorten this. I'll say number of ways EI can occur over total number of ways, or total number of all possible outcomes. Okay, so this is the formula for probability. So we have the rules of probability. The first one is that probability will always be between 0 and 1. So no one should find a probability that is 2 or 4 or 100. If you just find that your probability is not between 0 and 1, then your answer is definitely wrong. Then the sum of all probabilities is 1. Then we also have the complement of the probability. If you know that the probability of an event is, if you know that probability, then the probability that that event will not occur is known as the probability of the complement. So we put a bar on the E. So that is the probability of not occurring. It is just given by 1 minus the probability that that event will occur. Okay, so let's just have some examples. The probability of obtaining a head when a coin is tossed. So here we are saying that the probability is just given by number of ways that that event can occur over all the possible outcomes. So that means the probability of obtaining a head is just number of ways. How many heads do we have? We just have one. And all total outcomes, all possible outcomes, we have a head and a tail, so we have 2. So that means the probability of obtaining a head is 1/2. Okay. Okay, so the second one will have the probability of maybe obtaining. Okay, so let's have the probability of obtaining an even number. An even number when a die is cast. Okay, so this probability, I'll just shorten it as even number. Okay, so how many? We're looking at the probability that that event can occur over all the total possible outcomes. So now, how many even numbers do we have when on a die? We have, okay, of course, the faces are 1, 2, 3, 4, 5, and 6. Okay, so even numbers, we have a 2, 4, and 3. So we have 3 even numbers. The total possible outcomes are 6. So that means our probability, you just take that to its simplest form. You have 1/2. Okay, so that's how we obtain probabilities. Okay, so we have rules in probabilities. Okay, maybe actually these should be properties. There. These are properties. Okay. And now there, we look at the rules. So we have the first one, which is the addition rule. Okay. So, in the addition rule, we have that let E1 and E2, so these are events, elementary events actually. So let E1 and E2 be elementary events. Then the probability of E1 union E2 is just equal to the probability of E1 plus the probability of E2, then we subtract the probability of the intersection. E1 intersection E2. Okay, so that is the addition rule. Now, probability of E1 union, let's write that nicely. The probability of E1 union E2 is just the same as the probability of E1 or E2. So we use this interchangeably. We can use E1 union E2. It's the same as probability of E1 or E2. Okay, and the probability of E1 intersection E2 is just the same as the probability of E1 and E2. So the intersection, we're just talking about these events E1 and E2 occurring at the same time. Okay, so this is the addition rule, of course. If we want to find the probability of E1 union E2, which is the same as the probability of E1 event 1 or E2, we just get the probability of E1 and add to the probability of E2, and then finally subtract the intersection. Okay, so now let's have an example. So we want to find the probability of obtaining an S card or a red card. So this is just the probability of an S plus the probability of a red minus the probability of an S intersection red. Okay, so what is the probability of an S card? So you have to know how many cards are there in the deck of cards. So an S, you have 4 S's, because every number has 4 cards. Yeah, so the probability of an S will be 4. Okay, and so we're going to say this is equals to probability of an S is 4 over total number of cards 52 plus how many cards are red. So in a packet of cards you find that there are 26 red cards over 52 minus how many will be S's and will also be red. So the S's will always be 4, 2 black and 2 red. So the red cards which are both S's and reds will have 2 over 50. Okay, so you can compute that and find the answer. All right, so you can as well find the probability. Okay, so you can compute that. So this is the first one. You can as well find the probability that a card is not an S, not S, or red. Okay, maybe let's start with red or not S. So the probability of red cards is 26 over 52 plus the probability of cards which are not S's. So only 4 cards will be S's. So how many are not S's? So you have 52 minus 4, which is 48 over 52. And now we're going to subtract the ones that are not S's and red. Okay, so then we're going to find that from the 48, so the 48 are not S's, and half of them will be black and half of them will be red. So half of 48 is 24 over 52. Then you can compute that probability as well. Okay, so the other thing that we move to is mutually exclusive events. Okay, so events E1 and E2 are mutually exclusive if they have no common elements. So elements or events that have no common elements are known as mutually exclusive events. So we are saying E1 intersection E2 is supposed to be 0. So whenever I've asked you to find, to check whether the events are mutually exclusive or not, just check the intersection. If the intersection is 0, then it means that those events are mutually exclusive. Okay. So that is how we find mutually exclusive events. So such examples of such events, I can say maybe voting for two parties. So if you have in an election, if you have party A and party B, you can either vote, you can just vote for one, you can't vote for both. So there is no intersection. You can't vote for both of the parties. Okay, so those events, voting for part A and voting for part B, are mutually exclusive events because they have no intersection. Okay, now the other rule that we use in probability is known as okay, actually I can just say this is the subsection in probability known as conditional. Okay, so conditional probability, here we are looking at an event occurring given another. Okay, so for example, if you know that if you see from the weather report that it is going to rain, what is the probability that you are going to carry an umbrella? So your carrying of an umbrella actually depends on the weather forecast. So in conditional probability, we say that the probability of event 1 given, so we use the slash to denote given, which is the condition. Probability of event 1 given event 2 is just given by the probability of event 1 intersection event 2. So you get their intersection and divide by the probability of the condition. Okay, so here the probability of E2 is always greater than 0. Okay, we can also say that the probability of E1 given E2 is just simply also number of events that E1 intersection E2 can occur over the number of events that event E2 can occur. So both formulas give you the same answer. Okay, so we have an example. In this example, we are given a contiguous table. So you'll be seeing tables like this. This gives us just the characteristics. Okay, so the table presents results of 1,000 households in terms of purchase behavior for ZESCO units. Okay, so there are people who planned to purchase, okay, so you just plan, okay, and there are people who actually purchased. Okay, so then there we have yes and no, and we have the total. So we have 200 there, 100, 50, 650, 250, 750. We also have totals there, 300, 700, 1,000. So this table just simply implies that you have people who planned to purchase, and the way here, the ones that planned to purchase, you can see this column, this 250 or planned to purchase because they have a yes, okay, there, and this 750 did not plan. But for those that actually purchased, 300 actually purchased and 700 did not purchase. So you have those two, okay. Now let's find the probability that a household planned to purchase. Okay, so I'll say planned to purchase. Okay, so these are all the values that are saying yes here, planned to purchase, and it's 250 over all possible outcomes, which is 1,000. Okay, now how many, let's find the probability of those that planned and purchased. So these ones, we have a yes under planned and a yes under actually purchased. So where these two meet, okay, so we have a 200 there over total number of possible outcomes is 1,000. Okay, so this is how we get the probabilities. Now let's find out the conditional probability. Those that actually purchased, given that they planned. So those, we want to find the probability of those that actually purchased given that they planned. So according to the formula for probability, for conditional probability, okay, so we can just say this is n E1 intersection E2 over n E2. Okay, so E1 here is actually purchased and planned to purchase. So those that actually purchased and planned to purchase, so these are here, yes, they have yes under planned to purchase and they have yes under actually purchased. And those, the number of ways that can occur is 200. Okay, the condition is planned to purchase. So how many planned to purchase here? Planned to purchase is 250. Okay, so that is our probability. Just take it into the lowest terms and you're going to find 0.8. Okay, Now we move to independent events. Okay, so independent events are just events that are influenced by the occurrence of another. So here we have that the occurrence of one event does not influence. Okay, so actually for independent, they don't influence the occurrence of one event does not influence the occurrence of another. But for dependent, you find that actually they do affect, they do influence each. Okay, for dependent event, you find that the occurrence of one affects the probability of the occurrence of another. Okay, so I think here, the occurrence of one event does not influence the probability, so there should be probability here. The probability of the occurrence of the other. Okay, so one thing that you have to know for independent events is that the probability of E1 given E2 is just equal to the probability of E1. So the occurrence of event 1 given E2 is just the probability of E1. The occurrence of event 2 doesn't affect the occurrence of event 1. Okay, so that's one thing that you have to remember. Okay, so let's have an example. Okay, suppose we toss a fair die. Let B be the event that a number less than or equal to 4 is observed, and A be the event that an even number is observed. Okay, so the probability of B, which is the number less than 4, less or equal to 4, will be 4 over 6, which is 2 over 3. And the probability of A, which is an even number, is just 3 over 6, which is 1 over 2. So the probability, now the question is that are events A and B independent? Okay, so remember we have to use this statement there. The probability of B given A, or A given B, is supposed to be the probability of A, or the probability of B given A is supposed to be the probability of B. So therefore we need to find the intersection. The number is less than 4 and it's also an even number. So you have less or equal to 4 and also an even number. You just have two numbers there. 2 over 6, which is 1 over 3. Now let's find the probability of B given A. Okay, so you know that this is the probability of A intersection B over the probability of the condition, which is A. Probability of A given B is 1 over 3 divided by the probability of A, which is 1 over 2. Okay, so this is 1 over 3 divided by 1 over 2, which is just 1 over 3 times 2 over 1, and it gives you 2 over 3. And remember, this 2 over 3 is actually just the probability of B. So if this statement is satisfied, the probability of B given A is just the same as the probability of B. Then these events are independent. Okay, so we'll end here, and we'll then look at lecture 4. Okay, thank you so much.